Good Lord. Okay. So anyway, whatever, they missed the first minute. Um, the you have to watch the units on these. So the one of the ones that you have to really watch is like the molar mass. So when we normally get molar mass, um, so say for example, we do the molar mass of water, H2O is 18 grams per mole. Okay, so molar mass we usually get in grams per mole. In order to plug it in here and for everything to cancel out the way that we want it to, we actually need the molar mass in kilograms per mole. So all you really need to do is you take the molar mass and you move the decimal 3 to the left. So like this for water would be like 0.18 kilograms per mole. So just make sure that whenever you put the molar mass into this specific equation, that you change the molar mass from grams to kilograms per mole. Okay. So it talks about the lower the molar mass, the higher the RMS speed for that gas at a constant temp. So there are two types of sort of molecular movement that they're talking about here: effusion with an E and diffusion with a D. The diffusion you're probably somewhat more familiar with, like if you guys remember from bio, there's like the diffusion of particles across the cell membrane, right? Or osmosis is the diffusion of water. So diffusion is the spread of one substance throughout a space or throughout a second substance. So like, stinky freshmen spray Axe in their hallway, and then eventually it like works its way down all the hallways and whatever. So that's diffusion. Those gas particles are moving through other gas particles and spreading over time. Okay. Effusion with an E is one that is a little different. It's the escape of gas molecules through a tiny hole into an evacuated space, usually through a tiny hole in something that's considered like a solid. So one of the best examples of this is a balloon. So if you blow a balloon up with air, like just normal air, not necessarily helium or something, although it does with those too, but so you just blow it up with air or whatever, and if you let it sit, over time, the balloon shrinks, right? It loses air on the inside if you let it sit there for long enough. So if you think about it, like, I don't think people really kind of like think about it in this term, but like the pressure inside the balloon comes from the molecules hitting the sides of like the walls of the balloon, right? If the balloon stays at the same temperature, like you don't shrink it by putting it in a freezer or something, if it stays in the same temp, then what that means is the particles inside are hitting the wall less often, which should mean there's fewer particles. So if the balloon doesn't become like untied or whatever, like how, if it's tied off and closed, like how does it all of us, not all of a sudden, but over time, how does it have fewer air molecules in it? And that's this. So essentially what happens in a fusion is you get your solid, whatever it is, like the balloon or whatever substance, you get the molecules, right? And then you get air molecules or something, some other molecules, some gas that are inside that are moving around, right? And what happens is they bounce off of the walls. That's what creates pressure, right? Well, every once in a while, one of those molecules will hit the wall or the solid or whatever it is just right, and it'll just kind of squeeze through and escape. So there's like little tiny holes in these solid materials that gas diffusion happens. So like in the balloon, there's little gaps in between the solid of the balloon. And when some of the air molecules, so air molecules, I mean, they're that's where the pressure comes from, right? The molecules are constantly bouncing off the walls and bouncing all over. Well, every once in a while, an air molecule will hit that hole just right and just poop, squeeze right through and escape the balloon. And what happens is over time, because of the continual strikes or whatever, you just get air molecules that are that hit that hole just right, and you get slowly over time you get air leakage, you get gas leakage out of it, and it reduces the amount in there. Okay. Does that make sense? So the other thing with this is, uh, okay, so you can calculate the rate of effusion, basically like how quickly or slowly a gas will effuse out of something. Um, so uh, these are actually doing a rate of effusion between two things, between like two gases or whatever. Um, it's talking about the relative rate of effusion, blah, 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 blah. Only those molecules which hit the small hole will escape through it. Therefore, the higher the RMS speed, the more likely that a gas molecule will hit the hole. So let's think about this two ways. One, if the molecules are traveling faster, that means they're hitting the walls more often, right? So just because it is hitting the walls more often, the chance that it hits the hole is going to increase just by sheer number of chances that it has. Does that part make sense? Like it just has more chances, so the likelihood of it actually escaping is higher, right? Um, and then the second part of it is if everything is at the same temp, the reason that a molecule would be going faster is because it's smaller. If everything's at the same temp, the smaller a molecule is, the faster it'll travel. It's kind of like think of it like vehicles. If you've got two vehicles of different size, like you got like a little like Prius and you got a full size truck. If you were to feed them the same amount of gas, the same amount of energy, the Prius would go faster because it takes less. It's smaller, so it takes less energy to get it like physically moving, right? Um, so if you've ever been stuck behind a semi at a stoplight, you know how that goes. Like it takes forever to get moving, right? So the smaller the molecule is, the faster it'll go, which means it'll effuse faster as well, usually. Okay, so these are the equations. I highlighted the green here because those are instead of me writing the variables out the side, they're listed right here. So basically, you get molar mass 1 and molar mass 2 from two different gases, and then you get effusion rates R1 and R2. Now, notice the equation is R1 over R2 equals the square root of M2 over M1. So it's flipped. The molar masses are flipped under there. Okay. You can also, instead of the rates, you can set it equal to the RMS speeds, the U's, U1 and U2. Okay. So those are the equations. Diffusion is faster for light gas molecules. So this is diffusion, not effusion. Diffusion going throughout. Diffusion is significantly slower than the RMS speed. Diffusion is slowed by collisions of gas molecules with one another. So again, if you think of, well, and they give the perfume bottle example. Like the actual example that I used, it says it takes a while to detect the odor, but the average speed of the molecules at 25 degrees Celsius, which is basically room temperature, is about 1,150 miles per hour. So why don't you smell it immediately, like as soon as it's released? Well, that's because it's bounced, like the molecules that you smell, the little chemical gas molecules that you smell, they're bouncing off of stuff constantly, right? So it's not a straight line. It's not like shooting straight down the hallway. They'll travel in a straight line, but they're going to hit other molecules and bounce and deflect back and then hit off the walls. And so um, it's, I mean, the analogy I think of is like, I think about somebody who's like super drunk trying to walk somewhere. Like, they don't walk in a straight line, so it takes them forever to get anywhere. They're like leaning on the wall and they're weaving and whatever. So it's not like they don't travel in a straight path. So it takes them a lot longer to get anywhere, you know? Um, okay. They give you a definition of what's the mean free path. We're not going to deal too much with it, but you should just know that like the average distance traveled by gas molecules between collisions. Mean refers to kind of like average. Free means not being obstructed by anything, the path. So it's the amount of distance before one molecule from one collision to another, basically, when it's not being collided or impacted by anything. At sea level, the mean free path for air molecules is about 6 times 10 to the negative 6 centimeters. So that's kind of interesting a little bit because that's actually a number that we're like centimeters is a measurement that we can be somewhat familiar with. So if you think about it, that's this. So I'm trying to think what would, so milli would be, um, would be like that, right? What would, how many, what's not nano, what's the, it's been a while since I've looked at those. What's the one that's negative 6? Anybody remember?
Micro.
Oh, micro, yeah, thank you. The micro, so, oh, sorry. Centi would be, so this would be negative 3. So negative 6 would be micro. So that'd be like 0.06 micrometers. So, I mean, it's super small, but like, that's actually like, it's an amount that we can imagine. We're not talking like something like the number of atoms or like 10 to the 23rd or whatever. You know what I mean? Like that's, um, compared to the size of atoms, that's actually a significant distance between them. That's why, I mean, that's, we talk about having a lot of empty space between gas molecules. That kind of shows that. So, okay. Any questions on this part of it? All right. So I'm going to separate my videos.